What is the highest temperature that can be reached in the universe? Absolute zero is 0 Kelvin, you know that, minus 273 degrees Celsius. But what about the maximum temperature? 100,000 Kelvin? A million? A trillion? No, exactly 142 nonillion Kelvin. Nonillion is not a number we hear very often. Let me put it this way. Million, billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, and after that comes nonillion. If we absolutely must write it down, we're talking about a number like this. This temperature is known as the Planck temperature, and it is thought that the universe reached it only once. When? Of course, during the Big Bang. But to truly grasp this concept so that our minds can actually comprehend it, we need to continue the journey we've talked about before. A journey toward absolute zero, down to the atomic level, to that theoretical point where motion ceases entirely. And in this challenge, an intense and relentless struggle by scientists awaits us. The lowest temperature ever naturally observed on Earth occurred in August 2010 in Antarctica, measured at minus 94.7 degrees Celsius. This was not a direct measurement, but data obtained from NASA satellites, because at such a temperature, estimates suggest that a normal human, without extra protection, could survive for only about 3 minutes. Inhaling air that cold could be instantly fatal. Scientists searching for absolute zero once organized expeditions to the South Pole about 100 years ago, but of course, they couldn't even come close. The real steps toward absolute zero would first be taken in laboratory environments by liquefying gases. And at this point, the first name we encounter is James Dewar, who worked at the Royal Institution. In a public lecture in 1891, commemorating his predecessor Michael Faraday, he said that even approaching absolute zero by 5 degrees would increase our knowledge of the properties of matter to an incredible extent. James Dewar is one of those figures in the history of science who wasn't particularly well liked, largely because of his excessive ambition. But even if that ambition was somewhat selfish, it also became a driving force behind extremely important discoveries. His starting point, of course, was the legacy of Michael Faraday, who 70 years earlier, working in the same laboratory, had shown that gases like chlorine and ammonia could be liquefied under pressure, producing artificial cold for the first time. And Dewar's first question was this: was this method of liquefying gases using pressure valid for all gases? Could all gases be liquefied? When it came to so-called ideal or non-liquefiable gases, such as oxygen, nitrogen, and hydrogen, he hit a wall. No matter what he did, no matter how much pressure he applied, these gases simply refused to liquefy. Faraday, an intellect far ahead of his time, with an extraordinary intuition for the laws of nature, believed in practice and experimentation, and had said that this should be possible. With the tools available to him, he had managed to liquefy various gases and reach temperatures as low as minus 130 degrees Celsius. And that, in fact, was where the secret lay, in the cold itself. In 1873, Dewar would finally get an answer to the wall he kept hitting. Theoretical physicist van der Waals explained why these ideal gases did not liquefy. By accounting for molecular size and the forces between molecules, he showed that these gases had to be cooled below a certain critical temperature before pressure could liquefy them. In other words, even ideal gases could be liquefied, but only if they were sufficiently cooled. Thanks to this insight, oxygen and then nitrogen were successfully liquefied. Humanity had now reached temperatures close to minus 200 degrees Celsius for the first time. But the next stage, the next gas, was far more difficult: hydrogen. To liquefy hydrogen, temperatures had to drop to around minus 250 degrees Celsius. Whoever achieved this would become a superstar of the era. Dewar described this challenge with a metaphor: the hydrogen mountain, a massive peak that had to be climbed, and planting the flag at its summit became the greatest goal of his life. But where there is a challenge, a scientific nirvana, scientists are never alone. There will always be others who want to reach that summit, the most beautiful race of humanity, a race toward truth. And standing opposite Dewar was a young Dutch scientist, Heike Kamerlingh Onnes. Onnes actually had great respect for Dewar, but Dewar, well, let's just say was a bit irritating. He didn't exactly share the same feelings towards Onnes, and when Onnes decided to build a very large laboratory, Dewar became even more irritated. When Onnes took charge of the physics laboratory in the small Dutch city of Leiden, he was only 29 years old. At the opening ceremony, he openly declared his goals to a large crowd. He would become a pioneer in gas liquefaction and make the Netherlands known on the international scientific stage. Such a visionary approach was truly extraordinary at the time, a man in his late 20s saying he wanted to elevate his country through science. Onnes ran his laboratory like a factory, producing his own equipment and tubes in-house. He gathered science-obsessed young people, known locally as the Young Men in Blue Aprons. He would later go on to found a technical education school that is still operating today. In this sense, Dewar and Onnes were very different personalities. Dewar conducted his work in extreme secrecy, while Onnes shared his laboratory's progress with the world through a monthly journal. Dewar relied purely on experimentation, while Onnes planned every step theoretically before acting. Yet both adopted a similar approach to gas liquefaction. They would follow the same path to liquefy hydrogen, step by step, moving from one gas to another, from higher temperatures to lower ones. They applied pressure to the first gas and passed it through a cooling tube immersed in a coolant, liquefying it. And as you know, when a gas liquefies, it cools. That liquid then became the coolant for the next gas. Each newly liquefied gas cooled the next one in line. At the final stage, when they reached hydrogen, the goal was to compress it under pressures 180 times atmospheric pressure, using the cooling provided by the previous gases. This would bring temperatures down to an astonishing minus 252 degrees Celsius, just 21 degrees above absolute zero. But such pressures carried enormous risks. In Dewar's laboratory, many explosions occurred. Several assistants lost their eyesight due to flying glass. Yet when you look at Dewar's notes, you only find records of damaged equipment, no mention of the assistants who lost their eyes. In Leiden, Onnes faced similar dangers. Due to repeated complaints, he even had trouble with the police. Eventually, the laboratory he had opened with such great hope was shut down and sealed for 2 years because of explosion risks. And in the race to climb Hydrogen Mountain, Dewar now took the lead. By 1898, Dewar had been trying to liquefy hydrogen for 20 years. It was time for an all-out attempt. Using liquid oxygen, he cooled hydrogen gas to minus 200 degrees Celsius, increased the pressure to the limit, and opened the final valve. All eyes were fixed on the tube at the end of the vessel, which was on the verge of bursting. Then, suddenly, liquid began to flow. Dewar had done it. After 20 years, he had successfully liquefied hydrogen. He had reached the summit of Hydrogen Mountain. Victory was his. He should have been the happiest man in the world at that moment. But he wasn't. Why? Imagine dedicating your entire life to climbing what you believe is the highest mountain. You're the first to reach the summit. You stand there, at the top, and then you look ahead and see an even taller mountain. That's exactly how Dewar felt, because standing before him was a much higher peak, Helium Mountain. A newly discovered noble gas, and to liquefy it, temperatures had to fall to just 5 degrees above absolute zero. A new challenge. Dewar immediately set to work, but there was a problem. Helium was extremely difficult to obtain in sufficient quantities. It had only recently been discovered and was thought to exist mainly in the sun. Ironically, the chemists who discovered helium, Lord Rayleigh and William Ramsay, worked in a neighboring laboratory. But remember, Dewar wasn't exactly popular. He often dismissed their work, and as a result, he couldn't obtain helium from them. This is where our young scientist Onnes stepped in. Using his connections, he managed to gather enough helium and got to work immediately. He may have lost the first battle, but he was determined to win the war. Meanwhile, Dewar's bad luck continued. An assistant accidentally opened the valve of a tube containing his accumulated helium, releasing it all in an instant. By 1908, Honest was nearing the end. He gathered his entire team in the laboratory, rehearsed the procedure several times, evacuated all the air from the equipment, and began the experiment. After a long process, hydrogen liquefied, the temperature kept dropping, and finally, looking into the lower tube with a lantern, Honest saw it: liquid helium. He had reached the summit of Helium Mountain. He became the first human to approach absolute zero so closely, reaching minus 268 degrees Celsius. For this extraordinary achievement, he was awarded the Nobel Prize. This story, filled with ambition, failure, and struggle, reveals the relentless spirit of scientists. It also proves something else. The struggle never truly ends. Every goal reached reveals a new one. Every answer gives birth to a new question. Science is not a race toward a finish line. When you arrive, the curtain doesn't fall. Unexpected challenges are always waiting. Nature is always one step ahead of us, always holding another mystery. Ons would experience this as well. After liquefying helium, he immediately began studying how matter conducts electricity at extremely low temperatures. And at one point, he observed something astonishing. Just 4 degrees above absolute zero, the electrical resistance of mercury suddenly vanished. Conductivity skyrocketed to an extraordinary level. Ons had to invent a new word for this phenomenon: superconductivity. But that is a story for another time. And as always, until we meet again, I'm glad you're here. With love.